Recording. Happy Friday! We're going to be talking about attitude sensors and actuators today. So let's start out with sensing technologies. Before we have control, we need to know where we are in space. So that's why I want to talk about this first. Classifications of sensing. So there's remote sensing and there's in situ sensing. Remote sensing is looking at something that's far away, maybe it's not that far away, but looking at something that's not where you are, seeing it, collecting electromagnetic radiation from it, converting that signal into usable data, and then processing that signal. In situ sensing differs in that instead of looking at something that's disparate from you, you're measuring something that is at your location. In situ means, I think it means in, like right here. So the process is different from remote sensing in the highlighted steps. Instead of looking at something, you travel to a location. Instead of seeing it and collecting EM radiation, you're measuring it in situ. You're collecting the physical phenomena with a range of different techniques, instruments. And then like remote sensing, you can convert that signal, whatever that physical phenomena signal is, and then process it. And I have two examples down here of what a remote sensor would be like and what in situ sensing would be like. So here you can see the demonstration that, an Earth sensor or horizon sensor, you are looking at something. Whereas a magnetometer needs to be in the magnetic field, and then it interacts with some mechanisms, some electronics to induce current that you then measure. So hopefully the process within the sensor itself gives you some signs of whether it's a remote sensor or an in situ sensor. Okay. So now let's look into types of each. For remote sensing, we can detect the Earth's limb, so that's an Earth sensor. We can detect the sun with a sun sensor, and we can detect the stars with star sensors. Here I have an STK diagram of a satellite that's detecting all three at once. And you can see that geometrically, they are facing the different phenomena that they want to detect, and they're all at these specific angles. And you can also see that their fields of view are also not overlapping. That's not necessarily a requirement. That is a good thought process when designing in your structures and mechanisms where to place these sensors. For in situ sensing, we've got magnetometers, which measure the magnetic field, inertial measurement units, which measure acceleration. Sometimes IMUs can also incorporate a magnetometer, and they also commonly incorporate gyroscopes, which measure angular velocity. We can also use global positioning systems, or GPS, for position. All right, let's dive into an Earth or horizon sensor. What you're seeing here has been on the last few slides, so you should be pretty familiar with it. But what exactly is this sensor and what does it see? So typically, these Earth or horizon sensors are cameras. They can be of in the visible or IR range, and they collect a pixel map, just as any kind of camera would, and it is looking for Earth's limb. So here you can see a very nice picture of Earth. Now some of these questions, why don't we approach this one first? There are infrared range Earth horizon sensors, and the question is, would infrared emissions from the sun interfere with these sensors? So yeah, indirectly, any kind of infrared emission, not specifically from the sun, but maybe even from the Earth could interfere with these sensors. What you're trying to calculate or see from the sensor is a distinct line or edge that you can draw in this pixel map. And you can already see in this picture that maybe the atmosphere, some thermal emission can blur that line. Even the pixel resolution can get you a better or a worse reading depending on how many pixels you have. Now let's go up here. So would there ever be a case where the moon is used for out-of-the-window sensing? And absolutely, great question. There is a paper out there that's used in research. It was published about 5 years ago called Interplanetary Optical Navigation, where a mission was scoped around traveling from the Earth to the moon. And it would make total sense if while you're traveling to the moon that you look towards the moon and use it as a reference location or landmark. So absolutely, it's a great idea to use the moon if it is useful to your mission, to your unique mission. Using the moon wouldn't make as much sense, say, if you were traveling much farther away into deep space. Another thing about horizon sensors, are these sensors used on more advanced controls compared to 1U CubeSats? Actually, horizon sensors are probably one of the more coarse and simple sensors. So it would be used on missions that are simpler, that are smaller, because all that it is a little camera and some processing afterward. So we are seeing miniature cameras these days that easily fit within CubeSats. The one that Neutron 1 is using is like that big. The one that's on the Artemis CubeSat, that camera could even be used as an Earth or horizon sensor. It could be dual use, which would be pretty neat. All right, sun sensors. Sun sensors, the most widely used for spacecraft attitude, are similar to Earth sensors. As the name implies, a sun sensor finds the sun and determines its direction with respect to the spacecraft body frame. So here I have an image. Of course, it's very self-explanatory, but what I want you to notice here is that this sensor can only give 2 dimensions fixed on attitude without another point of reference. Here is a physical manifestation of a fine sun sensor. And what you'll see here is there's this window that the ray goes through. So this aperture and then this offset detector at the bottom allows this sensor to detect the angle of incident rays into the aperture. So using just a bit of geometry, you can figure out what angle the sun is from this boresight axis. Okay, I'll let you absorb that for a little bit. What else do I want to say? Within sun sensors, there are coarse sun sensors, which are on the Artemis CubeSat kit, where it's just a photodiode. It's just measuring the amount of solar flux that's coming through. And there are these fine sun sensors, which give you more information, not only magnitude, but direction as well. You can use, in the textbook, you should have seen these pyramidal sun sensors that kind of take advantage of different faces getting a different proportion of light. And so you can do that on the Artemis CubeSat kit as well. If you have a coarse sun sensor on different faces of the CubeSat, then that itself is like a scaled pyramidal sun sensor. So you can be creative. The solar panels even can be used as coarse sun sensors. All right, star sensors or star trackers. So here I have a depiction of a satellite looking at stars. But this time, star trackers can detect 3 degrees of freedom, or 3 axes of attitude orientation. Here is the anatomy of a sample star tracker, where the real sky up here, where there are stars that you're trying to observe, there's usually some kind of baffle where you want to protect the electronics inside from getting too much light. So any kind of noise that comes from diffraction or scattering can get reflected into this baffle, these edges, and get reflected back out. So you get a clean signal in. This works. This is simply put, there is a camera, a very high resolution camera that takes an image of the sky with stars in it, and given different constellation patterns that are on a star map. So here, software including star catalog, a star tracker is loaded with a star catalog. And within that star catalog, there are all labels of the strength of brightness of each star and how far away each star is. So intuitively, for humans on Earth looking at the sky, we can look at constellations. In fact, I'll show you. I have a poster of the celestial sphere. So we can recognize bright star constellations. A star tracker with a star catalog pretty much formalizes this recognition process where it identifies star patterns based off of bright pixels that it captures from the night sky. We look at the sky and it's just oh, okay, this is really cool. Polynesian wayfinders on their way to the Hawaiian Islands used the stars to navigate across the ocean. So they would use a star map. And I hope I say this right. It was on the Hokulea boats. So this is pretty much like a Western version, a formalized technological version of using the stars for wayfinding, where we're using computers for higher precision attitude resolution. What else do I want to say? Typically, these sensors are the most precise and they give you the most degrees of freedom. But the disadvantage is that they are usually more expensive. They are harder to test in a facility, and they're a little bit bigger in volume. So on the high-tide satellite, the Earth sensor and the sun sensor are about this big, whereas the star sensor, the star tracker, is a bit bigger because of this baffle that needs to be incorporated. Okay, now let's move on to in situ sensors. So there are magnetometers that take advantage of the existence of a magnetic field to measure what the local field is. So there's Earth's global field, but you're only sampling at a distinct point in that field. So that local magnetic field where you're sampling will be measured by the spacecraft, and given something like a magnetic field model that is loaded onto the spacecraft, you can figure out based off of that measurement where you are in space. But that measurement is going to be non-unique, as in that there are multiple points in orbit that you could be, so you need another measurement typically on top of a magnetometer to understand precisely a unique location that you are in space. So I already showed this picture on the bottom left. On the top right is another manifestation of a magnetometer. And you can also see magnetometers in chip form, like here. So I'll answer a couple questions. How do magnetometers deal with potentially disorienting anomalies like that linked here? So what's linked here is probably the South Atlantic anomaly. The South Atlantic anomaly is this, this pretty much hole in the magnetic field above the South Atlantic Ocean. So yeah, that is an anomaly, but given that we've measured the magnetic fields of the Earth to what I would say is high precision, maybe we can deal with those higher order effects in the model. And even if we can't, I know that satellites, as they're passing over the South Atlantic anomaly, when you're in the eye of the South Atlantic anomaly, there's a lot of radiation that blasts the satellite and can interrupt operations. So at that point, you can, before you approach the South Atlantic anomaly, maybe you could go into safe mode and shut down your instruments and major hardware, go into kind of a sleep. And then once you exit out, you can turn things back on. But those can be worked around. Do they have a filter for ignoring minor fluctuations in the Earth's magnetic field? So absolutely. When you were talking, or when you were reading about the determination chapter, there are filters that can deal with noise or perturbances in your measurements. So that's a good result. The sensor accuracy depends on the accuracy of the field model. Does the magnetometer need to be calibrated such that it counts for magnetic fields within the CubeSat? So yeah, I think that is a good way to go. A lot of magnetometers, as we've seen in spacecraft designs, have the magnetometer really far out on a boom so that you don't get as much electromagnetic interference from the spacecraft. But for our spacecraft, the magnetometer is embedded within pretty much the center of the spacecraft. So it would be good to get to do some ground testing and get a profile of what the magnetic field would look like when we have all of our electronics running. Another design decision could be that you place your magnetometer farther away from the electronics so there's less interference and you don't have to deal with that calibration step. Okay, so another type of in situ sensor is a gyroscope. We did talk about gyroscopes last lecture in the terms of control, but you can also use gyroscopes to measure angular rotation. So one of the ways to do it is with a ring laser, where your angular velocity is going to contribute to, okay, physics lesson. Your angular velocity is going to contribute to this system, which is your gyroscope, and within the spacecraft, its frame is going to accelerate. Because it's in a non-inertial frame, the light is going to travel differently. And because the light is, the laser is going to travel differently, you can measure that difference and correlate that to an angular velocity of your system that's moving. Okay, there are other ways of measuring angular velocity, such as using these really microscopic devices that a tuning fork gyroscope uses some bending of a structure, and you measure that bending and correlate that with some angular velocity. Okay, the next slide, the inertial measurement unit, is actually going to incorporate a description of a magnetometer. So I'm going to play this video. Hold on. Okay, so let's look at this video.
Spring, which is confined to move along one direction, and fixed outer plates.
Okay, so this is a description of a MEMS, or and MEMS stands for microelectronic something to do with microelectronics. Anyway, so this is within a chip. There are these very tiny structures that, so you'll see here, if this chip, which is on a board, which is in the spacecraft, experiences acceleration, then there's this mass with springs that oscillates. And you can...
So when an acceleration in the particular direction will be applied, the mass will move and the capacitance between the plates and the mass will change. This change in capacitance will be measured, processed, and it will correspond to a particular acceleration value. Next is the gyroscope, which measures angular rate using the Coriolis effect when a mass is moving in a particular direction with a particular velocity, and when an external angular rate will be applied, as shown with the green arrow, a force will occur, as shown with the blue arrow, which will cause perpendicular displacement of the mass. So, similar to the accelerometer, this displacement will cause change in capacitance, which will be measured, processed, and it will correspond to a particular angular rate. The microstructure of the gyroscope looks something like this: a mass that is constantly moving or oscillating, and when an external angular rate will be applied, a flexible part of the mass would move and make the perpendicular displacement. Okay, now let's explain how the magnetometer works. It measures the Earth magnetic field by using Hall effect or magnetoresistive effect. Actually, almost 90% of the sensors on the market use the Hall effect, and here's how it works. If we have a conductive plate like this and we set current to flow through it, the electrons would flow straight from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow and the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means that if we put a meter now between these two sides, we will get some voltage which depends from the magnetic field strength and its direction. The other 10% of the sensors on the market use the magnetoresistive effect. These sensors use materials that are sensitive to magnetic field, usually composed of iron and nickel. So when these materials are exposed to magnetic field, they change their resistance. Okay.
Yes, great description. Did you all hear that? Okay, great. So that was a great description of how these circuits, these tiny little sensors, work to measure acceleration, angular rate, and magnetic fields. You can look at something like this, or if you see 9DOF, the 9 stands for the 3 degrees of freedom from acceleration, 3 from angular rate, and 3 from magnetic field. If you see 6DOF, minus the magnetic field. Here is, if we go back in time, here's the inertial measurement unit used by the Apollo program. So we've gone quite a way going from something large and bulky like this to this little chip. Okay. Finally, for in situ sensors, I'm going to talk about global positioning systems, GPS. Here is a GPS unit, pretty tiny nowadays, but how do they work?
Your phone to receive. Each GPS satellite broadcasts a navigational message towards Earth which contains an extremely accurate timestamp, which is obtained through an atomic clock which is on board these satellites. And the satellites also broadcast their position at the time of broadcast, with all GPS signals broadcasting at 1.5752 GHz and 1.2276 GHz. These two bits of information allow you to work out your position on Earth. With these satellites all sending exceptionally accurate time down to Earth, your phone or GPS receiver can compare the difference of time between when the signal was sent to when it was received to work out the distance between you and the satellite. By multiplying this time...
Yes, okay, so that's how GPSs work. Question about GPSs. Is it possible to program an equation into the software for the IMU to account for drift? Or is a GPS better to have regardless of the space it takes up? So I think it's good regardless of the filter to have an unbiased opinion from another sensor. So the IMU can cross-reference with the GPS, or it can cross-reference with, say, the star tracker's 3-degree of freedom attitude estimate. For a little example, the IMU measures angular rate. Angular rate is a derivative of attitude. So by using the star tracker's attitude, you can get rid of the integration errors of the IMU's measurement. Because IMU, angular rate, integrate angular rate is attitude. Okay, to close our little section about choosing sensors, the way that you choose sensors for your mission is you need to know your exact mission parameters. For your missions, for example, you're Earth observing and you're looking for specific phenomena, so you need to know the resolution necessary to measure those phenomena. You should record all known design specifications of the satellite. Consider the range of technology that will be used in the system, and take into account the key performance criteria that your spacecraft needs to manifest. So I've got tables of the different sensors and their typical accuracy with pros and cons for each one. So let's see. Something that I should note here is that arc minutes are a sub-measurement unit of degrees. So one arc is going to be a degree, and a minute is so 1/60th of that arc. So this would be 1/60 degrees. You'll also see arc seconds, and arc seconds are 1/60th of a arc minute. So Earth sensors, even though it says 0.1 degrees and this is 1 arc minute, are actually the most coarse of all of these sensors. And then it goes the sun. Oh, no, magnetic field is the most coarse, then Earth, then sun, then stars. Usually all by a magnitude. And then the IMU measures something like this amount of angular rate. Typically, what you'll see is the combination of many of these sensors. So for example, on high tide, there is one of each of these on the satellite. You can use all of them in conjunction to get one master estimate of attitude while also getting some angular velocity. But if you're strapped, like we are in the Artemis CubeSat kit, we have the magnetometer, we have an IMU, and we don't necessarily have a dedicated Earth sensor or a sun sensor, but we can get creative by using those solar panels or photodiodes as sun sensors and the camera as potentially an Earth sensor. Here's another table describing the same things with different numbers and specifying, for example, 2-axis measurements. Just a tiny note here, for a star sensor, if you get 1 point, you can get 2-axis of estimate, but if you have multiple stars, you can get all 3 degrees. Okay. For sensor criteria, what you want to consider for each sensor when applicable is its field of view. So it's that cone of vision. Accuracy, which we talked about in the last slide. Environmental characteristics, which include operating temperature, radiation tolerance, and vibration limits. Mass and volume, power consumption, update rate, and angular resolution. Here are the sensors on the Artemis CubeSat kit. And what the team has done is listed as much of the sensor criteria as is known. So yeah, hopefully this will get you started. I can't wait to see what you've decided for your system. Okay, sensor configurations. So earlier we talked about picking particular sensors, and I discussed how in HiTi we have all of them. I'll take note that, let's see, it would be nice to get 3 degrees of freedom from your attitude sensors. Now, this can be achieved in many different types of configurations where you can just have a star tracker, or you can layer a sun sensor with a magnetometer, which you've seen in the triad determination algorithm. Sun sensor with a magnetometer. You could also throw in there an earth sensor. You'll see here that the configuration on this satellite is to use magnetometers, 2 star trackers, gyroscope, sun sensors, magnetorquers, GPS receivers. So you can go overboard. I wouldn't say overboard is the right word, but you can add redundancy to your system in case one fails and in case you want to get an even more precise measurement. More measurements equals higher accuracy and precision. By using 2 or more star sensors located around a spacecraft, the system can determine its attitude in 3 dimensions. Would this be the preferred method for deeper space missions, since it could be done anywhere in space and doesn't require a specific orientation? So although there are 2 star trackers in this configuration, and although deep space spacecraft, can have more than 2 star trackers, the disadvantage to star trackers is that they are sensitive to a saturation of light. You can actually damage the detector that is within the sensor if you, for example, expose it to the sun, or if it points towards Earth and all of that albedo comes back at you. So I wouldn't say that it's exactly a preferred method. As always, do the trade, but star trackers are certainly very, very much used for precise applications, especially if you're going into deep space. Your spacecraft is probably going to be larger and you can spare the volume that a star tracker needs. Okay, answer all the questions.